Right now, as you read these words, you are experiencing one of the most mysterious and fundamental features of reality, the relentless forward flow of time that carries you from past through present toward future in an inexorable march that seems as natural as breathing. You remember yesterday, but not tomorrow. Eggs break but don't spontaneously reassemble. Your coffee cools down but never heats up on its own. Every moment of your existence unfolds within a temporal landscape that appears to have a built-in direction, an arrow that points steadily from past to future with absolute certainty. But here's what's truly mind-bending. According to the fundamental laws of physics, time has no preferred direction whatsoever. Newton's mechanics, Einstein's relativity, quantum mechanics, even the standard model of particle physics, all of these theories treat time as completely symmetric. Every equation works equally well running forward or backward through time. If you filmed any fundamental physical process and played the movie in reverse, it would look just as physically realistic as the original. Yet somehow, from these time-symmetric laws emerges the most asymmetric feature of our reality, the arrow of time that gives meaning to cause and effect, that separates past from future, that makes memory possible while keeping the future unknown. The universe somehow knows which direction time should flow, creating a cosmic orientation that governs everything from the decay of radioactive atoms to the expansion of space itself, from the formation of memories in your brain to the ultimate fate of every star in the cosmos. What if I told you that this temporal direction emerges from one of the most profound principles in physics, the inexorable increase of entropy, the universe's tendency toward maximum disorder? That the arrow of time points towards states of higher entropy, not because of some cosmic law requiring forward time flow, but because there are vastly more disordered states than ordered ones, making the direction toward chaos statistically inevitable rather than physically mandated. The discovery of entropy as relationship to temporal direction represents one of the most elegant solutions to one of physics' deepest paradoxes. How can time-symmetric fundamental laws create time-asymmetric experienced reality? The answer lies in recognizing that while the laws themselves show no temporal preference, the initial conditions of our universe were extraordinarily special, a state of such low entropy that the subsequent evolution toward equilibrium creates the appearance of temporal direction through purely statistical processes. This statistical arrow of time explains why entropy increases, why information spreads from concentrated to dispersed states, why complex structures form and then decay, and ultimately, why consciousness can form memories of the past while remaining unable to directly perceive the future. The universe doesn't know which direction time should flow through some cosmic consciousness. Instead, temporal direction emerges from the mathematical inevitability of statistical evolution, from rare ordered states toward common disordered ones. But the implications extend far beyond thermodynamics into quantum mechanics, where the process of measurement appears to introduce irreversible temporal asymmetry into otherwise reversible quantum evolution. The collapse of quantum wavefunctions, the decoherence of quantum superpositions, and the emergence of classical reality from quantum foundations all seem to prefer forward time evolution in ways that connect quantum mechanics to thermodynamic time asymmetry. Recent discoveries in cosmology have revealed that the universe's expansion itself provides a cosmic arrow of time, with space growing larger and matter becoming more dispersed as cosmic evolution proceeds from the hot, dense Big Bang toward the cold, dilute heat death predicted for the far future. This cosmological arrow aligns with thermodynamic evolution, suggesting that time's direction operates constantly across all scales from quantum to cosmic. The relationship between consciousness and temporal direction creates some of the deepest puzzles in physics and philosophy. Why do conscious beings experience temporal flow as movement from past to future? How does the brain's information processing create the subjective experience of temporal passage? Why can consciousness remember the past but not the future? And how does this asymmetric memory relate to the fundamental physical processes that govern temporal evolution? Tonight, we are going to explore how the universe creates temporal direction without requiring any fundamental temporal asymmetry in physical laws. You'll discover why entropy always increases, how quantum measurements create irreversible time evolution, and why cosmic expansion aligns with thermodynamic evolution to create consistent temporal orientation throughout the universe. We'll journey from the statistical mechanics that explains everyday temporal asymmetry through quantum decoherence theory that reveals how classical reality emerges from quantum foundations to cosmological models that connect the Big Bang's low entropy to the ultimate heat death that awaits cosmic evolution. You'll understand how consciousness fits into this temporal framework and why your subjective experience of time reflects objective physical processes operating throughout the universe. You'll see how modern physics has unified previously separate arrows of time, thermodynamic, electromagnetic, cosmological, and psychological, into a coherent framework where temporal direction emerges from the universe's evolution from improbable initial conditions toward inevitable thermodynamic equilibrium. This unification reveals that time's arrow is unimposed by mysterious cosmic forces, but emerges naturally from the mathematical structure of statistical evolution in systems with finite information capacity. The practical implications extend from understanding aging and decay processes to developing quantum technologies that exploit temporal asymmetry for computation and communication. The fundamental research explores whether temporal direction might be manipulable through exotic matter configurations, quantum engineering, or cosmological interventions that could potentially reverse or alter the arrow of time itself. If you're fascinated by the mystery of why time flows in one direction, despite fundamental physics being time-symmetric, why entropy increases throughout the universe, and how consciousness experiences temporal passage within a cosmos that statistically evolves from order toward chaos, subscribe and hit thumbs up. And here is a question that takes on new meaning when considering temporal direction. If you could experience time flowing backward, watching effects precede their causes and remembering the future while forgetting the past, would you still recognize it as time, or would it become something entirely different? Comment below. I'll pin the most insightful answer because understanding temporal direction might be key to understanding existence itself, but we're getting ahead of ourselves. To understand how the universe determines temporal direction, we first need to examine our everyday experience of time as passage and ask why this experience seems so fundamental, yet proves so mysterious when examined through the lens of modern physics. Now let's begin this journey into the heart of temporal mystery, where we'll discover that the universe's knowledge of time's direction emerges not from cosmic consciousness, but from the elegant mathematics of statistical inevitability operating throughout reality. Chapter 1. The experience of temporal flow. Every moment of conscious existence unfolds within the streaming present that moves relentlessly from past toward future, creating the fundamental asymmetry that structures human experience and makes temporal direction seem like the most obvious feature of reality. Yet this subjective experience of temporal flow presents one of the deepest mysteries in physics and philosophy. How does the brain create the impression of movement through time when physics describes time as a dimension through which we might move rather than something that moves through us? The psychological experience of temporal flow involves multiple interconnected cognitive processes that create the illusion of a moving present moment. Working memory maintains information about recent events while gradually fading older memories, creating the impression that the past recedes into increasing distance. Attention focuses on present sensory input while anticipating future events through planning and prediction, mechanisms that make the future feel approachable but uncertain. This cognitive architecture creates what philosophers call the specious present, a psychological window of approximately 2 to 3 seconds within which events appear to occur simultaneously, despite being separated in physical time. The specious present enables conscious integration of sequential events into coherent experiences while maintaining the sense that consciousness exists at a moving boundary between determinate past and undetermined future. The neural mechanisms underlying temporal experience involve distributed brain networks that process different aspects of temporal information through specialized but interconnected systems. The hippocampus encodes episodic memories that provide the sense of personal temporal history, while the prefrontal cortex enables future planning and temporal reasoning. Circadian rhythm generators in the suprachiasmatic nucleus coordinate biological time with astronomical cycles, creating the physiological foundation for temporal orientation. But the subjective experience of temporal flow goes beyond cognitive processing to include the fundamental asymmetry of memory and anticipation that gives psychological time its directional character. Memory provides detailed information about past events, while future events remain uncertain and probabilistic, creating an information gradient that aligns with thermodynamic processes operating throughout the universe. This alignment suggests deep connections between consciousness and fundamental physical processes that govern temporal evolution. The philosophical problem of temporal experience involves reconciling subjective temporal flow with objective physical time as described by modern physics. Einstein's relativity treats time as a dimension in spacetime where all moments exist simultaneously in the block universe structure, making the moving present an apparent illusion rather than objective feature of reality. Yet conscious beings consistently experience temporal passage, despite theoretical arguments that such passage cannot be fundamental. Different theories attempt to explain this apparent contradiction between subjective and objective time through various mechanisms. Presentist theories maintain that only the present moment is real, making temporal flow an objective feature of reality rather than subjective illusion. Eternalist theories accept the block universe, but explain temporal experience through psychological mechanisms that create the impression of movement through static temporal structure. The relationship between consciousness and time becomes particularly mysterious when considering how temporal experience enables goal-directed behavior, moral responsibility, and personal identity across time. Conscious beings can plan future actions based on past experience while taking responsibility for previous decisions and maintaining continuous personal identity despite constant physical and psychological change. These capabilities require sophisticated temporal cognition that seems to transcend simple information processing. Recent neuroscience research has revealed that temporal experience involves prediction mechanisms that constantly generate anticipations about immediate future events while comparing predicted outcomes with actual sensory input. These predictive processes create the sense of temporal flow by maintaining dynamic models of changing environmental conditions that enable adaptive responses to evolving situations. The brain's temporal processing also involves multiple timescales operating simultaneously, from millisecond-level sensory processing through circadian rhythms to lifetime memory consolidation. These nested temporal processes create hierarchical time consciousness, where immediate perceptual present embeds within longer temporal. Context is personal history, social relationships, and cultural inheritance that extend far beyond individual lifespans. Language provides another window into temporal cognition through tense structures that enable communication about past and future events while maintaining shared understanding of temporal relationships. The linguistic universality of past, present, future distinctions across human cultures suggests that temporal asymmetry represents fundamental cognitive architecture rather than arbitrary cultural convention. The development of temporal consciousness in human children reveals the gradual emergence of sophisticated temporal cognition from simpler temporal sensitivities present from birth. Young children gradually develop abilities to understand causal relationships, plan future actions, and maintain autobiographical memory that creates coherent personal temporal narratives extending across their developing lives. Cultural variations in temporal conceptualization demonstrate that while basic temporal asymmetry appears universal, specific temporal frameworks vary significantly across human societies. Linear time consciousness, common in Western cultures, contrasts with cyclical time concepts in many traditional societies. While different cultures emphasize different temporal orientations from ancestor-focused, past orientation to future-focused technological planning, the aging process provides a natural experiment in temporal consciousness as brain changes associated with aging modify temporal experience through altered memory consolidation, processing speed changes, and shifting temporal perspective that makes time appear to accelerate as people age. These changes reveal the biological foundations of temporal consciousness while highlighting the intimate relationship between neural function and subjective time. Pathological conditions affecting temporal experience offer additional insights into the neural mechanisms underlying normal temporal consciousness. Patients with hippocampal damage lose the ability to form new episodic memories while retaining working memory, creating severe disruption of normal temporal experience that isolates consciousness within immediate present. Schizophrenia can disrupt temporal sequence processing and causal reasoning, leading to disordered temporal consciousness. Meditation and contemplative practices provide systematic methods for examining temporal consciousness through disciplined attention to present moment experience. Advanced practitioners report accessing states of consciousness where normal temporal flow appears suspended or transformed, suggesting that ordinary temporal experience represents one possible mode of consciousness rather than an inevitable feature of awareness itself. Psychoactive substances can dramatically alter temporal consciousness through effects on neural systems involved in temporal processing. LSD and psilocybin can disrupt normal temporal sequence processing while creating experiences of temporal expansion, compression, or fragmentation that reveal the constructed nature of ordinary temporal experience. The relationship between temporal consciousness and creativity involves sophisticated temporal cognition that enables artists, musicians, and writers to manipulate temporal structure in ways that create aesthetic experiences extending beyond ordinary temporal limitations. Musical composition involves creating temporal structures that guide listener experience through carefully orchestrated temporal relationships, while narrative arts manipulate temporal sequence to create meaning through temporal patterning. Dream consciousness provides another altered state where normal temporal relationships become highly flexible, with dream narratives often involving impossible temporal sequences while feeling coherent within the dream state. This temporal flexibility in dreams suggests that waking temporal consciousness involves active, cognitive processes that maintain temporal coherence rather than passive reception of objective temporal flow. The question of whether animals experience temporal consciousness comparable to human temporal awareness remains largely open, though evidence suggests that many animals possess sophisticated temporal cognition, including episodic-like memory, future planning, and temporal sequence learning. The evolution of temporal consciousness might have emerged gradually through increasing complexity of temporal processing capabilities rather than sudden emergence of uniquely human temporal awareness. The implications of temporal consciousness research extend into artificial intelligence development, where creating machines with sophisticated temporal cognition represents one of the major challenges in developing truly intelligent systems. Current AI systems can process temporal sequences and maintain temporal models, but lack the integrated temporal consciousness that characterizes human experience, suggesting that temporal consciousness might be essential for general intelligence. But examining temporal experience raises fundamental questions about the relationship between subjective time and objective, physical time. How does the brain's temporal processing relate to the fundamental physical processes that determine temporal direction throughout the universe? Why does consciousness experience time flowing in the same direction that entropy increases? And how do psychological and physical arrows of time align so perfectly? Chapter 2. The Entropy Imperative. The second law of thermodynamics stands as one of the most profound and universal principles in physics, declaring that entropy, the measure of disorder and randomness in any system, always increases in isolated systems, never decreases. This relentless march toward maximum disorder provides the fundamental mechanism by which the universe determines temporal direction, creating the arrow of time that points steadily from ordered past toward disordered future through the inexorable statistical evolution of cosmic structure. Entropy emerges from the statistical mechanics of large systems containing enormous numbers of particles, where the overwhelming likelihood favors evolution toward states with higher probability rather than lower probability. In any macroscopic system, there exist vastly more disordered arrangements than ordered ones, making evolution toward disorder statistically inevitable, despite the underlying physical laws showing no temporal preference. The mathematical foundation of entropy uses the Boltzmann formula S equals K log W, where entropy S equals Boltzmann's constant K times the logarithm of W, the number of microscopic arrangements, microstates, that correspond to the same macroscopic appearance, macrostate. This formula reveals why entropy increases. Systems naturally evolve toward macrostates with larger numbers of corresponding microstates because such states are exponentially more probable. Consider the classic example of gas molecules in a container. Initially confined to one half of the container, the gas molecules can arrange themselves in relatively few ways while maintaining the concentrated distribution. Once released, the molecules can spread throughout the entire container in enormously more ways, making uniform distribution vastly more probable than continued concentration. The entropy increase accompanying gas expansion reflects this statistical transition from improbable concentrated states toward probable dispersed states. This statistical interpretation explains why entropy increases without requiring any fundamental temporal asymmetry in physical laws. The molecules obey time-symmetric equations of motion, but the overwhelming statistical likelihood favors evolution towards states with higher entropy. If we could somehow reverse every molecular velocity simultaneously, the gas would contract back to its original concentrated state, but such precise reversal becomes practically impossible for systems containing astronomical numbers of particles. The practical impossibility of entropy decrease in macroscopic systems emerges from the exponential scaling of probability differences between ordered and disordered states. For a system containing Avogadro's number of particles, approximately 1023, the probability ratios between ordered and disordered states involve numbers so large that spontaneous entropy decrease becomes effectively impossible despite being theoretically allowed by fundamental physics. This statistical inevitability of entropy increase creates the thermodynamic arrow of time that governs all macroscopic processes from melting ice cubes to stellar evolution. Heat flows from hot objects to cold objects because molecular arrangements corresponding to uniform temperature distribution vastly outnumber arrangements maintaining temperature differences. Chemical reactions proceed toward equilibrium because product states typically correspond to more molecular arrangements than reactant states. The connection between entropy increase and irreversibility becomes apparent when considering the Piaget-Ring-Lenoir information requirements for reversing thermodynamic processes. To reverse the melting of an ice cube, we would need precise information about the position and velocity of every water molecule at the moment of complete melting, then apply exactly the right forces to drive each molecule back to its original position. The information requirements for such reversal exceed any conceivable measurement or control capability. Biological systems present particularly striking examples of entropy's relationship to temporal direction through the irreversible processes of aging, growth, and death that characterize all living organisms. While living systems can temporarily decrease their internal entropy through metabolism and energy consumption, they inevitably increase the entropy of their environment by larger amounts, maintaining compliance with the second law while creating local order through global disorder increase. The thermodynamic arrow of time extends beyond terrestrial examples to cosmic scales through stellar evolution, galaxy formation, and the expansion and cooling of the universe itself. Stars burn nuclear fuel irreversibly, converting light elements into heavier ones while radiating energy into space, increasing cosmic entropy through processes that cannot spontaneously reverse. Galaxies form through gravitational collapse that converts gravitational potential energy into heat, further increasing cosmic entropy. The origin of the universe's low entropy initial state represents one of the deepest mysteries in cosmology because it appears to violate the expectation that initial conditions should be typical rather than special. The Big Bang began with matter and energy in an extraordinarily ordered configuration that enabled billions of years of subsequent entropy increase through structure formation, stellar evolution, and cosmic expansion. This past hypothesis, the assumption that the universe began in a low entropy state, provides the boundary condition that enables entropy increase throughout cosmic evolution while avoiding the problems that would arise if entropy were already at maximum values from the beginning. Without low initial entropy, there would be no arrow of time, no possibility for complexity or structure formation, and no opportunities for life and consciousness to develop. Fluctuation theorems in modern statistical mechanics have revealed precise mathematical relationships governing entropy behavior in systems far from equilibrium, demonstrating that while large entropy decreases remain exponentially unlikely, small temporary entropy decreases can occur with calculable probabilities. These fluctuations create brief violations of the second law that become increasingly unlikely as system size and time duration increase. The relationship between information theory and thermodynamics has revealed deep connections between entropy increase and information processing that extend the second law's implications into computation, communication, and memory formation. Landauer's principle demonstrates that erasing information necessarily increases entropy, creating fundamental limits on reversible computation while connecting information processing to thermodynamic processes. These information-theoretic insights illuminate how consciousness and memory formation relate to entropy increase through the irreversible processes involved in learning, memory consolidation, and decision-making. The formation of memories requires physical changes in neural networks that increase entropy while preserving information about past experiences, making temporal asymmetry essential for conscious information processing. The Maxwell's demon thought experiment illustrates the intimate relationship between information, entropy, and temporal direction by proposing a hypothetical intelligent being capable of sorting molecules to decrease entropy without performing work. Careful analysis reveals that the demon must erase information to complete sorting cycles, ensuring that total entropy still increases when accounting for information processing costs. Modern attempts to realize Maxwell's demon using sophisticated measurement and feedback systems have confirmed that information acquisition and processing require energy expenditure that maintains overall entropy increase. These experiments demonstrate that apparent violations of the second law through intelligent intervention actually confirm thermodynamic principles when information costs are properly accounted. Quantum thermodynamics has extended classical thermodynamic concepts to quantum mechanical systems, revealing how entropy increase operates in quantum contexts through decoherence processes that irreversibly Couple quantum systems to environmental degrees of freedom. Quantum entropy increase provides microscopic foundations for classical thermodynamic behavior while connecting quantum measurement processes to thermodynamic irreversibility. The arrow of time emerging from entropy increase provides a statistical rather than fundamental explanation for temporal direction, suggesting that time's arrow could theoretically reverse if systems evolved toward lower entropy states. However, the exponential improbability of large-scale entropy decrease makes such reversal effectively impossible for macroscopic systems, creating practical irreversibility from statistical principles. Future research in thermodynamics continues exploring the limits of entropy manipulation through advanced nanotechnology, quantum engineering, and information processing techniques that might enable unprecedented control over thermodynamic processes while remaining constrained by fundamental thermodynamic limits. These investigations might reveal new possibilities for exploiting thermodynamic principles while confirming the universal nature of entropy increase. The philosophical implications of entropy's role in determining temporal direction challenge deterministic views of causation while supporting probabilistic interpretations of natural law. The second law operates through statistical inevitability rather than causal necessity, making temporal direction emerge from mathematical relationships rather than physical forces while creating irreversibility through information-theoretic constraints. But understanding entropy as the source of temporal direction raises immediate questions about how microscopic quantum processes relate to macroscopic thermodynamic behavior. How does quantum mechanics, with its reversible wave function evolution, connect to irreversible entropy increase? What role does quantum measurement play in creating the thermodynamic arrow of time? Chapter 3. Quantum Time's Asymmetric Dance. Quantum mechanics presents a profound paradox for understanding temporal direction. The fundamental equations governing quantum systems are completely time-reversible. Yet quantum measurements appear irreversible, and quantum decoherence processes create the emergence of classical reality from quantum foundations through mechanisms that strongly prefer forward time evolution. This quantum arrow of time connects microscopic quantum processes to macroscopic thermodynamic behavior while revealing how temporal asymmetry emerges from the interaction between quantum systems and their environments. The Schrödinger equation, which governs quantum mechanical evolution, treats time symmetrically and permits wave functions to evolve backward as easily as forward through time. If we know a quantum system's wave function at any moment, we can calculate its state at any past or future time using exactly the same mathematical procedures. This time symmetry suggests that quantum mechanics imposes no fundamental preference for forward versus backward temporal evolution. Yet quantum measurement processes appear fundamentally asymmetric in time, with measurements causing irreversible collapse of quantum wave functions from superposition, states containing multiple possibilities to definite outcomes corresponding to specific measurement results. This wave function collapse seems to prefer forward time evolution. We can predict future measurement outcomes probabilistically based on current quantum states, but we cannot retroactively uncollapse wave functions to determine past quantum states from present measurement results. The measurement problem in quantum mechanics involves understanding how definite classical outcomes emerge from indefinite quantum superpositions through processes that seem to require temporal asymmetry, despite the underlying quantum equations showing no temporal preference. Various interpretations attempt to resolve this paradox through different mechanisms ranging from objective wave function collapse to subjective observer effects to many worlds branching that preserves quantum linearity. Quantum decoherence provides the most promising framework for understanding quantum temporal asymmetry by demonstrating how quantum systems inevitably couple to environmental degrees of freedom in ways that create effective irreversibility without requiring fundamental changes to quantum mechanics. When quantum systems interact with environments containing many particles, quantum coherence disperses throughout the environment in ways that become practically irreversible. The mathematical description of decoherence uses density matrix formalism to track how quantum information spreads from systems into environments through entanglement processes that preserve total quantum information while making it inaccessible to local measurements. This information dispersal creates apparent wave function collapse for local systems while maintaining global quantum coherence across system-environment combinations. Decoherence rates depend on environmental coupling strength and temperature, with larger systems in warmer environments producing faster decoherence that rapidly eliminates quantum superpositions and creates classical behavior. These decoherence processes operate asymmetrically in time because environmental interactions typically involve many body systems that follow thermodynamic evolution toward higher entropy states. The emergence of classical reality from quantum foundations through decoherence represents one of the most important examples of temporal asymmetry arising from statistical rather than fundamental processes. Classical behavior emerges when quantum decoherence occurs faster than quantum revival timescales, creating effective classical evolution that respects thermodynamic temporal direction while preserving underlying quantum time symmetry. Quantum measurement theory has evolved beyond simple wave function collapse models toward more sophisticated treatments involving quantum instruments, positive operator-valued measures, and quantum trajectories that provide detailed descriptions of measurement processes without requiring instantaneous non-unitary evolution. These advanced frameworks reveal how measurement-induced temporal asymmetry emerges from quantum classical interfaces rather than fundamental quantum processes. The quantum Zeno effect demonstrates how frequent measurements can freeze quantum evolution, while the anti-Zeno effect shows how measurements can accelerate quantum decay processes. These measurement-dependent evolution rates reveal intimate connections between quantum measurement frequency and temporal evolution that create non-trivial relationships between observation and temporal progression. In quantum systems, quantum thermodynamics has revealed deep connections between quantum mechanical evolution and thermodynamic processes through studies of quantum heat engines, quantum refrigerators, and quantum entropy production that operate according to quantum mechanical principles while respecting thermodynamic constraints. These quantum thermal devices demonstrate how quantum effects can enhance or limit thermodynamic performance while maintaining temporal asymmetry. The fluctuation theorem in quantum mechanics provides precise mathematical relationships governing entropy production in quantum systems driven away from equilibrium, demonstrating that quantum systems can exhibit temporary entropy decreases with calculable probabilities while maintaining long-term entropy increase. These quantum fluctuation theorems connect microscopic quantum processes to macroscopic thermodynamic behavior. Quantum entanglement creates non-local correlations that appear to transcend traditional causal relationships while maintaining consistency with relativistic causality constraints. The temporal aspects of quantum entanglement involve subtle questions about how entangled correlations develop over time and whether quantum non-locality might influence temporal direction through non-local quantum effects. Bell's theorem and experimental violations of Bell inequalities have confirmed that quantum mechanics involves genuine non-locality that cannot be explained through local hidden variable theories. These non-local quantum correlations exist within space-time relationships that respect relativistic causality, while creating quantum correlations that seem to transcend classical temporal sequences. The delayed choice quantum eraser experiments reveal how quantum measurements performed in the future can appear to retroactively influence past quantum evolution, creating apparent temporal non-locality that challenges conventional understanding of causality and temporal sequence. These experiments demonstrate quantum mechanical predictions while raising fundamental questions about temporal relationships in quantum mechanics. Quantum error correction provides mechanisms for protecting quantum information against environmental decoherence through encoding procedures that enable detection and correction of quantum errors without measuring protected quantum information directly. These quantum error correction protocols create possibilities for maintaining quantum coherence over extended time periods despite environmental coupling. Quantum computing exploits quantum superposition, an entanglement to perform computations that would be intractable for classical computers, while requiring sophisticated quantum error correction to maintain computational fidelity against decoherence processes. The temporal evolution of quantum computations involves careful management of quantum coherence to complete calculations before decoherence destroys quantum advantages. The relationship between quantum mechanics and consciousness involves speculative proposals that conscious experience might depend on quantum processes in neural systems, potentially creating connections between quantum measurement and subjective temporal experience. These quantum consciousness theories remain highly controversial, but suggest possible relationships between quantum temporal asymmetry and psychological temporal direction. Quantum field theory extends quantum mechanics to relativistic contexts where particle creation and annihilation processes create additional temporal asymmetries through mechanisms including Hawking radiation, Unruh effect, and vacuum fluctuation phenomena that prefer forward time evolution. These relativistic quantum effects connect quantum temporal asymmetry to cosmological evolution and black hole thermodynamics. The quantum arrow of time emerges from the combination of quantum decoherence, environmental entanglement, and thermodynamic evolution that creates effective temporal asymmetry from underlying time-symmetric quantum mechanics. This emergent temporal direction aligns with thermodynamic evolution while providing microscopic foundations for macroscopic irreversibility through quantum statistical mechanics. Future developments in quantum technology might enable unprecedented control over quantum decoherence and measurement processes, potentially allowing manipulation of quantum temporal evolution in ways that could reveal new aspects of quantum temporal asymmetry while remaining constrained by fundamental quantum mechanical principles and thermodynamic limits. The philosophical implications of quantum temporal asymmetry challenge classical concepts of determinism and causality, while supporting interpretations of natural law based on statistical inevitability and informational constraints. Quantum mechanics reveals temporal direction as emergent property of quantum environmental interactions, rather than fundamental feature of quantum dynamics. But quantum temporal asymmetry raises profound questions about the relationship between microscopic quantum processes and macroscopic classical behavior. How does quantum decoherence connect to everyday experiences of temporal direction? What role do quantum processes play in creating the classical world where thermodynamic temporal asymmetry dominates our experience? Chapter 4. The universe's memory problem information possesses a strange relationship to temporal direction that creates one of the deepest puzzles in physics. Information appears to be conserved in all fundamental physical processes, yet our everyday experience involves constant information loss through forgetting decay and the irreversible destruction of organized structures. This apparent contradiction between fundamental information conservation and experienced information loss reveals profound connections between memory formation, thermodynamic evolution, and the mechanisms by which the universe appears to remember its past while forgetting alternative possibilities. The principle of information conservation emerges from the reversible nature of fundamental physical laws, which require that complete information about any system as current state must be sufficient to determine both its past and future evolution. In classical mechanics, knowing all particle positions and velocities enables calculation of system evolution backward or forward in time with perfect accuracy. Quantum mechanics preserves information through unitary evolution that maintains total quantum information content despite redistributing it through entanglement processes. Yet this fundamental information conservation seems to conflict dramatically with everyday experience of information loss through numerous irreversible processes. Burned books cannot be restored to their original state by cooling the ashes. Scrambled eggs cannot spontaneously unscramble. Human memories fade and distort over time. These apparent information destruction processes suggest that information does not remain conserved in macroscopic systems despite theoretical expectations from fundamental physics. The resolution lies in recognizing that information conservation operates at microscopic levels, while information accessibility becomes severely limited through statistical processes that preserve total information while making most of it practically inaccessible. The information contained in burned book ashes remains conserved, but becomes dispersed among astronomical numbers of molecular configurations that would require impossible measurement precision to reconstruct. This distinction between information conservation and information accessibility explains how the universe can simultaneously conserve all information while appearing to lose most of it through processes that increase entropy. The second law of thermodynamics does not destroy information but rather disperses it throughout environmental degrees of freedom in ways that make information retrieval exponentially difficult despite remaining theoretically possible. Memory formation in physical systems requires mechanisms for encoding information in stable configurations that resist environmental perturbations while remaining accessible for later retrieval. Biological memory systems achieve this through neural network modifications that store information in synaptic connection patterns, DNA sequences, and protein configurations that can maintain encoded information across timescales ranging from seconds to lifetimes. The thermodynamic costs of memory formation and maintenance create fundamental limitations on information storage capacity and temporal persistence that connect biological memory to physical limits on information processing. Every bit of stored information requires energy to maintain organization against thermal fluctuations that would otherwise randomize stored patterns, creating ongoing energy costs for memory preservation. Landauer's principle quantifies the minimum energy required for irreversible information processing operations, demonstrating that erasing information necessarily increases entropy and requires energy expenditure. This fundamental limit connects information processing to thermodynamic evolution while explaining why memory formation involves irreversible physical changes that contribute to entropy increase. The cosmic information problem involves understanding how the universe stores information about its own evolution while maintaining consistency with thermodynamic principles that seem to require information dispersal. The universe must remember physical constants, initial conditions, and causal relationships that determine subsequent evolution while forgetting detailed microscopic information that becomes thermodynamically inaccessible. Black hole information paradox represents the most extreme version of the cosmic memory problem by questioning what happens to information that falls into black holes. Hawking radiation appears thermal and random, suggesting that information falling into black holes gets destroyed when black holes evaporate. However, information conservation principles require that black hole evaporation must somehow preserve all infallen information in the outgoing radiation. Recent theoretical developments suggest that black hole information gets preserved through quantum entanglement between falling matter and outgoing Hawking radiation, maintaining information conservation while making information retrieval practically impossible without access to the complete quantum state of all emitted radiation. This proposed resolution maintains fundamental information conservation while explaining apparent information loss through accessibility limitations. The holographic principle proposes that all information contained within any volume of space can be encoded on the volume S boundary surface, providing mechanisms for information conservation that transcend naive spatial limitations. This holographic information storage might enable the universe to maintain complete memory of all events while distributing information throughout boundary surfaces, rather than volume interiors. Quantum error correction provides biological and artificial systems with mechanisms for protecting information against environmental decoherence, through redundant encoding schemes that enable information recovery despite partial information loss. These error correction mechanisms create possibilities for maintaining information accessibility over extended time periods, despite thermodynamic evolution toward higher entropy. Digital preservation technologies demonstrate how information can be maintained across arbitrarily long time periods through active error correction and periodic refreshing that compensates for gradual information degradation. These technological memory preservation techniques reveal principles that might operate in biological systems and potentially in cosmological information preservation mechanisms. The evolution of biological memory systems from simple molecular storage mechanisms to sophisticated neural networks reveals how information processing capabilities can increase through evolutionary processes that create increasingly sophisticated memory architectures, capable of storing, processing, and retrieving larger amounts of information with higher fidelity. Epigenetic memory systems enable organisms to preserve information about environmental conditions across generations through heritable modifications to gene expression that do not involve DNA sequence changes. These epigenetic mechanisms provide examples of biological information preservation that transcends individual lifespans while remaining subject to gradual information decay through successive generations. Cultural memory preservation through language, writing, art, and digital technologies enables human societies to maintain information across many generations while creating cumulative information preservation that can exceed biological memory limitations. These cultural memory systems demonstrate how information preservation can be enhanced through cooperative preservation mechanisms. The relationship between memory and identity raises fundamental questions about how information preservation relates to continuity of identity across time. Personal identity seems to depend on memory continuity, yet memories constantly change through forgetting, reconstruction, and new experience integration. This suggests that identity involves dynamic information processing rather than static information storage. Artificial intelligence memory systems face similar trade-offs between information preservation and processing efficiency that characterize biological memory. Machine learning systems must balance comprehensive information retention against computational efficiency, leading to memory architectures that selectively preserve relevant information while discarding less important details. The cosmic memory landscape includes mechanisms ranging from particle decay processes that preserve conservation law information to cosmological parameter preservation that maintains consistency of physical constants throughout cosmic evolution. These cosmic memory mechanisms ensure that the universe maintains sufficient information to support continued coherent evolution while allowing enormous amounts of detailed information to become thermodynamically inaccessible. Future information technologies might enable unprecedented information preservation capabilities through quantum memory systems, artificial biological memory enhancement, and advanced error correction techniques that could dramatically extend information accessibility timescales while remaining constrained by fundamental thermodynamic limits. The philosophical implications of universal memory problems challenge assumptions about knowledge, identity, and temporal continuity while supporting views of reality based on information processing rather than material substance. Information conservation principles suggest that all experiences and events remain preserved in universal memory while becoming practically inaccessible through entropy increase. But understanding cosmic memory raises fundamental questions about the relationship between information, consciousness, and temporal experience. How does the universe's information preservation relate to conscious memory formation? Why does consciousness experience temporal asymmetry that aligns with thermodynamic information dispersal? What does universal information conservation mean for personal identity and individual significance? Chapter 5. Consciousness and the Direction of Now. The human experience of now, the perpetually moving present moment that seems to advance steadily from past toward future, represents one of the most intimate yet mysterious aspects of temporal experience. This psychological arrow of time appears to align perfectly with thermodynamic and quantum arrows of time, suggesting deep connections between consciousness and the fundamental physical processes that determine temporal direction. Understanding how consciousness creates and experiences temporal flow reveals profound insights into the relationship between mind and the cosmic mechanisms that govern time's passage throughout the universe. The neural basis of temporal consciousness involves distributed brain networks that integrate sensory input, memory retrieval, and predictive processing to create the seamless experience of temporal flow that characterizes normal awareness. The brain's temporal processing operates across multiple timescales simultaneously, from millisecond-level neural firing patterns through circadian rhythms to lifetime memory formation, creating hierarchical temporal architecture that enables sophisticated temporal cognition. Working memory systems in the prefrontal cortex maintain information about recent events while gradually releasing older information, creating the psychological impression that past events recede into increasing temporal distance. This memory decay process aligns with thermodynamic principles by moving information from accessible to inaccessible states, suggesting that psychological temporal asymmetry reflects fundamental information theoretic processes operating throughout the universe. The hippocampus plays a crucial role in temporal consciousness by encoding episodic memories that provide the sense of personal temporal continuity while integrating new experiences with existing memory frameworks. Hippocampal damage severely disrupts temporal consciousness, trapping patients within an eternal present where new episodic memories cannot form while existing memories remain accessible but feel disconnected from current experience. Predictive processing theories suggest that consciousness operates by constantly generating predictions about immediate future events, while comparing predicted outcomes with actual sensory input. This predictive architecture creates the sense of temporal flow by maintaining dynamic models of changing environmental conditions that enable adaptive responses to evolving situations while creating the impression of movement through time. The global workspace theory of consciousness proposes that temporal experience emerges from information integration processes that bind distributed neural activity into unified conscious experiences. This integration requires information flow across brain networks that operates asymmetrically in time, with current sensory input influencing future neural states, while past neural states influence current processing through memory mechanisms. Attention plays a fundamental role in temporal consciousness by selecting specific aspects of ongoing neural processing for conscious awareness while filtering out irrelevant information. Attentional mechanisms operate asymmetrically in time by focusing on present sensory input while using past experience to guide attention toward behaviorally relevant future events, creating temporal orientation that aligns with thermodynamic temporal direction. The development of temporal consciousness in human infants reveals the gradual emergence of sophisticated temporal cognition from simpler temporal sensitivities present from birth. Young children develop understanding of causal relationships, temporal sequence, and personal temporal continuity through processes that require integration of memory formation, predictive processing, and attentional control that mature throughout childhood and adolescence. Altered states of consciousness provide insights into temporal consciousness by revealing how various interventions can modify or eliminate normal temporal experience. Meditation practices can create states where temporal flow appears suspended or dramatically altered, while psychoactive substances can disrupt normal temporal sequence processing or create experiences of temporal expansion, compression, or fragmentation that reveal the constructed nature of ordinary temporal consciousness. The relationship between consciousness and free will involves sophisticated temporal processing that enables conscious beings to plan future actions based on past experience while taking responsibility for decisions that unfold across time. This temporal agency requires neural mechanisms that can integrate memory, prediction, and decision-making processes in ways that create the experience of authoring one's actions across temporal sequences. Quantum theories of consciousness propose that awareness might depend on quantum processes in neural systems, potentially creating direct connections between consciousness and fundamental quantum mechanical processes. These speculative theories suggest that quantum decoherence in neural systems might contribute to the irreversible aspects of consciousness that align with quantum temporal asymmetry. The hard problem of consciousness, explaining how subjective experience emerges from neural activity, becomes even more challenging when considering temporal consciousness. How does the brain create the subjective experience of temporal flow from neural processes that operate according to physical laws that show no fundamental temporal preference? This question touches the deepest mysteries about the relationship between mind and physical reality. Information integration theories suggest that consciousness corresponds to integrated information generated by neural networks, with temporal consciousness emerging from information integration processes that operate asymmetrically in time. The information integration required for conscious experience might naturally align with thermodynamic information processes that create temporal asymmetry throughout physical systems. Memory consolidation processes that occur during sleep demonstrate how consciousness and temporal asymmetry connect through irreversible neural changes that preserve information about past experiences while enabling future learning. Sleep-dependent memory consolidation involves transfer of information from temporary hippocampal storage to permanent cortical storage through processes that increase neural entropy while preserving behaviorally relevant information. The aging process provides insights into temporal consciousness by revealing how brain changes associated with aging modify temporal experience through altered memory formation, processing speed changes, and shifting temporal perspective. These age-related changes demonstrate the biological foundations of temporal consciousness, while highlighting connections between neural function and subjective temporal experience. Social temporal consciousness involves shared temporal frameworks that enable coordinated behavior across multiple individuals through language, cultural practices, and social institutions that create collective temporal orientation. These social temporal mechanisms suggest that consciousness and temporal direction connect not only through individual neural processes, but also through cultural evolution and social information processing. The relationship between consciousness and mortality creates profound temporal asymmetries through awareness of finite lifespan that influences decision-making, goal formation, and meaning attribution in ways that depend essentially on temporal direction. Conscious beings must navigate the tension between immediate temporal experience and awareness of temporal finitude that gives urgency and meaning to conscious choices. Dreams provide an altered state of consciousness where normal temporal relationships become highly flexible, with dream narratives often involving impossible temporal sequences while feeling coherent within dream consciousness. The temporal flexibility of dream consciousness suggests that waking temporal consciousness involves active cognitive processes that maintain temporal coherence rather than passive reception of objective temporal flow. Artificial consciousness research faces fundamental challenges in creating machines with temporal consciousness comparable to human temporal awareness. Current artificial intelligence systems can process temporal sequences and maintain temporal models, but lack the integrated temporal consciousness that characterizes human experience, suggesting that temporal consciousness might be essential for genuine artificial awareness. The evolution of consciousness might have been driven partly by advantages conferred by sophisticated temporal cognition, including future planning, causal reasoning, and temporal coordination with other conscious beings. These adaptive advantages of temporal consciousness suggest that consciousness and temporal direction evolved together through processes that created alignment between psychological and physical temporal asymmetries. The philosophical implications of consciousness and temporal direction challenge materialist accounts of mind while supporting views that consciousness plays fundamental roles in creating or accessing temporal asymmetry. The perfect alignment between psychological and physical arrows of time suggests deep connections between mind and cosmos that transcend simple neural information processing. But understanding consciousness and temporal direction raises profound questions about the nature of subjective experience and its relationship to objective physical processes. How does subjective temporal flow relate to objective temporal asymmetry? Why does consciousness experience time flowing in the same direction that entropy increases throughout the universe? What does this alignment tell us about the fundamental nature of mind and reality?